Hello everyone, my name is Ahmed and today I'm going to present about the role of system calls in secure process management, the critical interface between application and kernel. In the beginning, the call system is serve as a fundamental control interface between user-level applications and the operating system kernel. They act as essential gateways that allow user applications to request privileged operations safely and precisely. Operating through the user kernel privilege boundary, system calls profoundly influence process isolation, access control, and overall system reliability. Without this crucial layer, application would have unrestricted access to hardware, leading to severe instability and the complete elimination of process isolation. A minor validation error within a system call can result in a devastating consequences such as privilege escalation or memory corruption. The security of system calls is increasingly visual today, especially with the widespread adoption of virtualization, cloud computing, and contrast workload where robust isolation is paramount. So now, the system call architecture and flow are divided into many categories. First of all, invention. It's an application invokes wraps functions that trigger a CPU instruction, such as syscall, systems, or CVS. Mode switch. Execution simply switch from user mode to the more privileged kernel mode, facilitating direct hardware interaction. Moving to validation. The kernel identifies the system call number. Metaphysically validation all supply pointer and permission execute legitimately and safely. Execution. The requested function is executed within secure confines the kernel mode, accessing necessary system resource. Return. Results are safely returned to user space and execution revert to user mode. Now we have process control. Operation like fork, execute, exit, and wait manage the life cycle of process. Memory management. Such calls such as MMAP and PRK handle the allocation and the collection of memory resource of process. Files and 1 and 0 function like open, read, write, and close enable processes to interact with files and other I/O devices. IPS inter-process communication. Mechanism including socket shared memory and signals facilitate communication between disparate processes. Moving to security. Calls like set UID, CHMOID, and capabilities manage and enforce access privilege and security policies. Now we have system call and secure process management. Process creation, privilege, and separation. System calls such as fork, clone, and exec ensure that new process inherit necessary but strictly limited rights. Calls like setuid and capabilities rigorously enforce the principle of least privilege execution, preventing unwarranted access. Now we have access control enforcement. System calls are instrumental in enforcing various access control policies including discretionary access control, mandatory access control through mechanisms like SE Linux and AppArmor, and access control list permission check at the safe call boundary guarantee process only interact with the authorized resource. Isolation and protecting system calls underpin critical isolation mechanism. Process isolation, preventing process from arbitrary memory access via protect address space. Secondly, memory protection enforcing policies like ASLR and WS write SOR execute to thwart code injection attack. Secure IPC validation process identities and permission to prevent unauthorized inter-process communication. Key security vulnerabilities in SaaS calls. Rest condition TOC/TOU. Attacker exploits the critical time gap between security validation check and the actual user resource, leading to unintended access or modifying. Buffer and flows and point buffer flows and pointer attacks. This vulnerability arises from inadequate pointer validation allows malicious input to override kernel memory, potentially leading to system compromise. Privilege escalation. Facility or efficiency within system call handler can be leveraged by attacker to gain authorized evaluation or privilege within the system. Abuse of CSCall interface. This includes techniques like CSCall flooding code, denial of service tools attack, and side channel attack that infer sensitive information by observing sensitive behavior. Now we had modern security technique for system calls. System call filtering mechanism like SECOM BPF restrict process to a predefined safe subset of a system call. This significantly minimizes the attack surface by preventing malicious application from invoking dangerous or unnecessary operation. Now, capability-based security. This approach breaks down traditional root conflict into smaller granular units. The CAPNet admit processes are then guaranteed only the minimum necessary privilege and helps directly to the least privilege model. Sandboxing. Isolation framework including namespace, AppArmor, Steel, Linux, and iOS. And entitlements are extensively used in browser, mobile operating system, and containers. Strongly isolate applications, limit their potential impact in case of compromise. Virtualization-based isolation. Hypervisors and micro VMS introduce powerful separation between different workloads. This hardware-assisted isolation prevents cross-contamination and enhance the security posture of multi-tenant environment. Case study in major operating systems. Starting off with Linux. Implies architecture-specific physical table utilize C Linux, AppArmor System, and eBPF-based monitoring for fine-grained security policies and dynamic physical filtering. Windows. System calls are issued through NTDLL to the system service. This proprietary key feature include kernel patch guard and virtualization-based security. Moving to macOS, built on the Match microkernel architecture, leverages the seed-built sandbox system, robust code signing, and an extensive entitlement model for application security. Future research and innovation. Hardware-backed security. Increased focus on hardware-assisted isolation and security environment mechanism, leveraging trusted execution environment and other silicon-level protection. Reduced kernel interface. A growing trend toward verified micro-kernels and any-kernels aim to drastically reduce the kernel attack surface, enhancing overall system resilience. AI-based physical anomaly detection. Emerging research involves sophisticated AI-based models to detect anomalous system call patterns, identifying and mitigating malware behavior in real time. Next-gen architecture, development of zero-trust OS architectures, and advanced sandboxing physical virtualization techniques to build inherently more secure and resilient systems. And last and not least, the conclusion, safeguarding the digital core. A system called false representation and critical interface between user application and kernel operation. Their robust security directly underpins system stability, ensure process isolation, and determine system resistance to sophisticated attacks. Model protection mechanisms including sandboxing, capability-based security filtering, and virtualization have significantly strengthened System 4, security, creating more resilient computing environment. Ensuring rigorous and variable system 4 security will remain a favorite area of the research and involving of system complexly continues to escalate in our increasingly interconnected world. The ongoing challenge is to balance functionality with unyielding security. And thank you everyone for listening. Hope you enjoyed it. Thank you.